Okay, so remember we are looking, so variational setting, or variational approach if you want. Yeah, so this is, it's not the only way to apply stochastic analysis to the problem of Euclidean quantum field theories. It's the approach I choose to present in the lecture. There are other approaches using, for example, Langevin equation or other kind of SPDs, and represent the measure you're interested in. So again, okay, vaguely, abstractly, we are interested in a problem like this. So we have a base measure we want to perturb. Again, when we introduce the regularization, our problem has this form. And then I showed you one case where you remove the regularization and your problem has still this form. This is in 542, but this is an exceptional situation. So we have to, somehow the idea is that move away to this representation to have another way to talk about our measure nu, to describe it, which is more robust. Okay, so this was our Gibbs measure. You call this the potential. This in our application is the Gaussian free field, or some lift amplification of it, you will see later. And then what I said, so this is nu v, so nu v is a minimizer, just to recall where we were, okay? Is a minimizer. There are a lot of variational problems in this lecture, okay? So nu v is a minimizer of the following functional. This is the general setting. You don't need very much to, then this apply to every measure, and you just need the notion of, the entropy. So this is the relative entropy. It's the entropy you saw in the lecture. It's called relative because you have a base measure. Okay? This is the general form, and then if you minimize this object, okay, so this is the average of V with respect to nu. This is the entropy of nu with respect to V, and the minimizer is exactly that, okay? And then if mu is a Wiener measure, so the second step was on a Wiener space. So if nu is, if all the randomness is generated by a Brownian motion, essentially, think about, okay, so example mu is the law of a Brownian motion, finite dimensional, let's say, and then we had this, essentially this thing that if the entropy is finite, then in particular nu is absolutely continuous with respect to mu, and then in particular nu as the form. So I did something wrong the last time. So let me go back to. I think I want to precise a bit a moment. Just so to mu has this form. So what I call I can write mu. So mu has a form so that it has a density with respect to the measure mu, and this density is exactly Girsanov transformation with respect to some. So let's call the let's call the canonical process X. Okay, so this is the canonical process. Sorry, I will write bigger. Okay, this is just so canonical process on the probability space of mu. Okay, I don't want to introduce the notation. Okay, the mu has its own space, and then this is should be Wiener measure, means it's a measure on paths, and this is the canonical process. I just need to write the stochastic integral, and then you have u squared ds. Okay, so what is magic with respect to Brownian motion is this fact, okay, that any perturbation, any absolutely continuous perturbation of a Wiener measure has this form with respect to the filtration. Okay, this is not even true for simple random walk. Okay, you perturb a simple random walk in a very general way. There is no easy formula for the. Okay, so this is a structural requirement, and then this is now an exercise for you. Given this form of the density, you compute the entropy, at least formally. You have to pay attention, because if you take the log, you will see a minus 1/2 the integral of u squared appear, but then this stochastic integral has no average 0. Okay, so it will give a contribution in the limit. So try to do this exercise. So now you compute, now you compute the relative entropy of this measure, and you should find that this is 1/2 the average under nu of the L2 norm of the drift. Okay. Okay, it's almost this formula, but this minus become a plus because this object will give a contribution, because under this measure, x is not a Brownian motion anymore, but it got a drift. Okay, this drift exactly changes sign. Okay, so this is a representation of entropy, and then I use the, okay, and so now from these considerations, we got a first formula. So U is adapted. So this is adapted to the canonical process, okay? Because here you had the canonical process, then you find process adapted to the canonical process, which do this job. This is Girsanov theorem in a general form. And then if you compute now your functional, let's call this functional, I call it FV on nu. So if you compute FV on nu for this particular kind of nu, so you find is the expectation, so you will find, is the expectation under nu of V of x, so let me explicitate the canonical process, plus 1/2, so I was a bit incorrect, I put mu here, but it's actually nu. Yesterday I did a mistake, sorry. So you have a formula like this, which is almost what we want, but x is not a Brownian motion, remember under nu. So under nu, which is a Girsanov transform, under nu, x can be written as a Brownian motion, so let's call it W, plus a drift. And the drift is just the integral of U, okay? So you see x satisfy, so this x here is not a Brownian motion, but is a shifted Brownian motion, okay? So this become a control problem now, okay? You have a variational problem, a statistical mechanic problem, which become a control problem, because now the goal is to find, you have a Brownian motion, you want to push it in such a way that you minimize this plus that, okay? But if you push it too hard, this become big. So maybe you want to go in the region where the potential is small, but then you have to pay a price for that. So this formula is almost good and can be used to do many things, but somehow I prefer to use, so the subtlety is that now I will write a similar formula. The only difference is that U is, you see here the problem is that U is adapted to X. Okay, so it's not easy to use because what you know about what you want to study this variational problem. So what is the goal? Why I call this a stochastic analysis approach is that you have a Brownian motion. So you want to leverage the fact that under this measure nu, which is a general trial functional, you always have a new Brownian motion. So the Brownian motion, you know the law, you know everything, but of course, you see that if U is adapted to X, this becomes a differential equation, okay? Essentially, you have to imagine that I know very well W and I want to extract information from this equation. So this is a real equation, so it's difficult to study because for V is given by this process, so there's no regularity, it's not Lipschitz, it's not even Markovian, it's nothing, okay? So it's very difficult to study. So this becomes an SD. So this is, remember that this is somehow, this is some kind of equation like that. If I need to write it, is the xt is ut of x, but this could depend on an adapted way on the past. Okay, so and then there is the Brownian motion. Okay, so under nu you have an SD for the process. Okay, this is a control problem, and of course the policy in the control problem is a general policy, but the difficulty is that this way of thinking is very fast because I use only very known thing, but you have this problem that actually when you try to use it, it's difficult to estimate x from this control problem because here you have to put a functional of x. Okay, so Okay, if does not make sense to you, keep in mind that this is just, for me, a justification to introduce the Bouet-Dupuy formula, which has a more difficult proof, which I'm not going to do, which the only difference is that you optimize, instead of optimizing over u adapted to x, you optimize over the u adapted to a Brownian motion. So that's much easier. Okay, so in Bouet-Dupuy formula, what we have is that, sorry, let me call, yeah, so essentially, let me write it, so, yeah, it seems strange, so let me write the first time is essentially you control the logarithm, okay, so essentially the formula is a formula for this quantity, which is the logarithm of the denominator, essentially, which is called free energy. And this formula say that you have the inf over u over adapted control of the expectation, and here you use just mu, okay? I will not, yeah, so let me maybe write. So it's a similar formula, it's very similar, so you will have x plus I of u plus 1/2, but it's very different, okay? US squared, US squared, yes. Okay, so it seems very similar because this functional model is the same, because you see this object is like that. Under nu, this is a Brownian motion. Okay, the canonical process is a Brownian motion, and you shift the Brownian motion. The only difference in this formula from the formula you get by putting this inside here, in that u here is adapted to x, and here is adapted to x. So you say, okay, it's the same, but no, okay, because, okay, x here is the Brownian motion, while x here is not the Brownian motion, okay? So this is the full difference. Now, the control problem here looks like this, dxt, sorry, the control problem here, somehow is the control problem for this process, so this is the control, sorry, my note, yeah, let's use this notation, okay, this is, so the control problem now is that, sorry, actually, let me call it x of u. So you have a new process which satisfy dxt. So this is Brownian motion again, because we are under, here we have just to be under mu. So the first thing is that the measure does not change, while here you have to optimize over all the measures. So here your probability spaces is moving while you're optimizing. While here the probability space is fixed, you have a Brownian motion, and the control looks like this, okay? Looks like x, okay? But of course, okay, this is an SD. This has to be solved. Given w, you have to solve it. Here is not an SD, it's just an equation. I give you x, I compute this, I compute that, and I compute the control, okay? So it's completely trivial, and this is completely difficult, okay? And yeah, it seems, yeah, I mean, of course, it seems a very small detail, but when you try to apply this thing, it's matter, okay? So this formula, sometimes for many things, one can use also this formula, because maybe the drift, you see, it's a variational problem. If you want some control and you want to just plug in a given drift, maybe the drift is already of this form, so you are okay. Okay, but essentially this is more general. Okay, so this is the Bouet-Dupuy formula. Maybe, I mean, all the course is about this formula. So I think if you have a question, you should ask now about the formula, meaning, yeah, please.
Maybe just if you want to solve this optimization problem, is it really the case that you need to get controls that depend on the entire history?
Well, it depends in an adapted way. In general, yes, because this functional depends on the full history. Okay? Yeah. So, yeah. So actually, we will not use the formula in this form. I will show you. So if your function, typically, if your functional depend only the, let's say, the value of this process at the end time, then you can use dynamic programming, and you see that the optimal control is Markovian, for example. Okay, in that case you can simplify. actually, for any control, you can produce the Markovian projection and realize that the Markovian projection gives the same value for the value function, and you are done. Okay, but anyway, yeah. So, and in many cases, but I don't want to use this property because I don't gain anything about that. So I think I look at the optimization problem. This structure of Markovianity is not very useful for us. Okay. Or I didn't found very useful. But yeah, so let me remark if v of x, if v of the process is a function of, let's say, the terminal time, okay, some given time, then you can actually reduce your variational problem from 0t, okay, the problem localized on the interval 0t, because you don't have any incentive to shift the Brownian motion after that time, because you don't gain anything. So essentially you can forget. And the control ut of x can be taken Markovian. Okay, can be taken as some u of xt. Okay, are sufficient. So it's Markovian. Yeah, it's Markovian. So other questions about? I showed yesterday the other day an application to prove like Gaussian tails, but actually you can. This is an equality. So if you are smart enough, you can do anything. Also prove that some random variable is not integrable because you produce a competitor which goes to infinity. Well, you prove the inf has to go to infinity. Sorry, you cannot do. To prove an upper bound, sorry, okay, this formula is in this form. Let me rewrite. This is, I have all this minus because this is as the good interpretation in statistical mechanics. You want an energy and you want to depress the region where the energy is larger. So this is the reason of all this minus. And then this become an infimum. But in probability, sometimes you want to prove, variant. Okay, so variant, you just imagine if you want just to bound a random variable, like with the other sign. So this is convenient when you think about integrability. I want to prove this random variable is integrable, and then you have just to invert all the, no, we are not, to invert all the things. So here you have the potential with the plus, but then the entropy comes with the minus, okay? Okay, so, but this becomes now a maximization problem. Okay, to prove that this is integrable, you have to prove that there is no way for you to force the Brownian motion to force this object to be very large without paying a large price. Okay, this is difference.
Is this formula true for any others in marking? So in general, how much is possible to extend to other types of
No, yeah, so now, okay, this is a good question. The formula is as good as it is, but you see, the functional, that's the advantage of this general formulation, if you want, is that the functional is any functional of a Brownian motion. So if you can represent, we will do this actually very soon, if you can represent your object of interest as a functional of some Brownian motion, then you're done. Okay, so if you have an SD, it will also work because the SD, if you have a strong solution, is a functional of the underlying Brownian motion. So you just see, you don't apply this directly to, okay, if here you have, instead of having a functional of a Brownian motion, you have a functional of an SD, you represent the SD as a function of Brownian motion, and you use the same formula, okay? And actually, we will have not even SD, we will have a Gaussian free field, and we will represent very soon, actually right now, Gaussian free field as a functional of a Brownian motion, and I will use this formula. But I need a Brownian motion. I mean, we had some discussion. Probably there are extensions to Poisson processors or to other class of processors, but somehow I take the point of view that I like very much this formula, and I extract information from there. It works. I don't see any inconvenient. Okay, so it's not a universal tool, but it's a very useful tool. And nowadays, if you look in the literature, which cite our paper, I think there are various applications around of this formula, and it seems to be very useful. Especially, well, this formula, of course, is like stochastic control, so it's nothing new. The idea is how you can use this kind of approach to study problem in statistical mechanics. especially in continuous space. Okay, this is the idea. You transform a problem in probability into a problem of stochastic analysis where you can use pathwise methods. Okay, that's important. Okay, so this formula allows you to do from, okay, so this is probability, so this is probability, and this is stochastic analysis, if you want. Okay, so this is the main point. The title of the lecture is a stochastic analysis perspective, and this is the main tool. Okay, so let's go on. This was a recap and also precision about the formula. What I want to do now is to apply to our case. So application, okay, let's do it here actually, because it's more or less here. So let's apply to, yeah, I think in the note I made a jump. So now I will proceed a slightly different way. I want to, so application. So the rest of the lecture is essentially under this title, so how we apply this formula. So we need to find a Brownian motion in our problem, and the idea is the following. So take, so let's look first to 542, okay? Consider 542. So this is the first problem, okay? I will, on the torus. On T2. Okay, so I will not, this is like I showed you that the theory exists via Nelson argument, so let's try to do an argument instead using this formula. Okay, so I have the Gaussian free field. So what now I need to find this Brownian motion, and essentially the easy way to do that is the following. So let me do it slowly. You consider a process Bt, which is a cylindrical Brownian motion on L2 of T, okay? So what does it mean? It means simply, so this process now, it's a process which depends on time, and let's say I just need time between 0 and 1, I need just some time. It's a process which depends on time, so meaning cylindrical Brownian motion is a Brownian motion with a spatial dependence, and the covariance structure is given by the inner product in L2. Okay, you can do this for every Hilbert space. Given an Hilbert space, you have a bilinear form, which is positive, and you can use this as covariance structure. So in theory, you want to think this is a process with values in the Hilbert space, so in value L2, but then this will not work. You realize it has to be realized in a space of distribution. Is what is called. So what is the covariance structure of this process? It will look like this. If you take, so it will have two parameters now, okay? Sometimes I forget about this, but essentially from now on, I'm looking a random field. So all my random variables are essentially random field, and I just explicitate most of the time only the time dependence, okay? So let's look, it's a Gaussian process, it's a martingale for its own filtration, given by the time parameter, and then the covariance is just like Brownian motion, and then in this vector, it's a vector of Brownian motion, infinite dimension, and then here you have the delta function. Okay, so it's a singular random field, and so it's a white noise in the space variable, so it's independent in every point. This is a delta function, and in the time variable is a Brownian motion, okay? You can think of it, a way to realize it is simply, for example, you take just Fourier, okay? You take Fourier variable and you take a bunch of Brownian motion for every Fourier variable, okay? So this is a way to realize it, for example, okay? So these are IID, complex Brownian motion, okay? So very easy, and if you don't like to work with continuous object, you have just a bunch of Brownian motion and then this transformation, okay? You can think of it just as a bunch of independent Brownian motion in Fourier space. Okay, now we have to cook out, you say, okay, what you do with that? So I just took a lot of Brownian motion, and now I just look at this process. Yeah, now let me change the notation. So I define WT because this is the notation in the lecture notes. I define Wt as this operator applied to Bt. Okay, so I just color, okay, I put something in front here which go 1 over k squared. Okay, so this is, if you want, again, Wt of x is just the sum over k. You have Fourier transform, but now you have 1 plus k squared, 1/2, and then you have the same Brownian motions. Okay, so nothing exceptional. Now, the point I want to make is that now Wt, the covariance of this process, so, okay, let's write it in this way. Now you compute the covariance of this process and you realize that is, well, in time you didn't do anything, so it's a Brownian motion, but in space you have colored with this thing, and then you get exactly the covariance of the Gaussian free field. Okay, so at time 1, the law the law of W1 is the Gaussian free field with variance 1. Okay, actually at every time is, so the law at time t is t times the Gaussian free field. Okay, just t is the variance. Yeah.
To have conjugation relation between the beta.
Yeah, these are say complex Brownian motions, but meaning that. Yeah, to have it real. Yeah, you're right. I just didn't care because I will never use this representation again. So essentially, yeah, should be the complex conjugate of the other one. The zero mode has to be real and so on. Yeah, sure.
On the previous equation, the stochastic differential equation, is there some type of invariance this U should some invariant property for the U independent of V?
Here.
No, on the stochastic analysis on the right, on the main equation.
Okay.
Is there some type of invariant property U can satisfy independent of V because it's adapted to the Brownian motion?
What do you mean invariance property?
Like, I don't know, the Brownian motion is a property with respect
to rotation, like it's a vector valued. Well, this norm certainly is invariant under rotation, but of course the functional then this, yeah, sure. I mean, this formula contains everything I know about Brownian motion, more or less, or interesting property like hypercontractivity. Yeah, so my usual hobby is if I have a problem, I try to use this formula the first thing first, okay? It was invented, actually this formula is invented for large deviation because it transforms a problem in probability into a variational problem, which is in the same form of the end result in large deviation, which you should have rate function, okay? So this was, I will maybe try to use it. We will do large deviation for Euclidean field theory and you will see that it works very well. Yeah, so let's go back here. So here I just came up with a bunch of, so if you want to forget about the cylindrical Brownian motion, if you don't know about it, just define this object like this. And it has this property. It's a martingale because it's a sum of a bunch of martingales. It's Gaussian. And the value at time 1 is exactly my Gaussian free field, okay? This is arbitrary. Next week I will do differently for a different problem because I need, it's more complicated, I need more structure. You see, so what we know already, so I know a lot of things about this. You can just guess what would be the pathwise regularity of W. In time, it behaves like a Brownian motion, so it will be order 1/2. In space, it behaves like the Gaussian free field. Like this is really a product of these two covariants, so there is computation are more or less trivial to prove, you know, or all you need to know to prove that this object belong almost surely to Holder function 1/2 minus in the interval 0t, let's say, with value in the Holder space C minus, we are in 2 dimensions, so I can do C minus kappa on the torus. Here minus kappa, if you want, you can write it like this, okay, for any kappa positive. So this is the regularity of this object, okay? It's Brownian in the t variable, and it's Gaussian free field 2 dimension in the space variable. Okay, you know everything. So it's not a function, okay? This will be a problem later, so I will use a different regularization later on where when I increase time, this increases also the irregularity, okay? The only property I need is just one marginal of this process has to be my target, my target. Okay, let's go on with this. Otherwise, so I will skip a lot of technical details, so bear with me. Ask question if you want. Try not to ask pedantic question, but if you're not sure, please ask before or not asking. If you want to really define details, I will bother you 3 hours later, okay, in private. Okay, so we have this, and now think about the problem. Yeah, think about the problem for 5.4. Essentially, for 5.4.2, what we did, it was, okay, we had the exponential of Vt phi with respect to the Gaussian free field. Okay, so essentially, we need to compute this. Okay, so this is the GFF. And remember, Vt was the integral over my domain of the regularization. So let me write explicitly the regularization of Et to the power 4, and it has been weak renormalized. Okay, again, weak renormalization is just that you construct this polynomial of order 4 using this Gaussian and its covariance. So it's, and then you integrate overall space. Okay, now I have the GFF, but I have another, now I have a way to represent, interesting way to represent the GFF. It's just, I transform this formula into a formula where here I put my W at 1, okay, because W1 has the same law. And this is also GFF. This is completely arbitrary, okay, this is a trick, okay, you don't understand why it's not intrinsic. I could have constructed W in many ways, so that at W1, at time 1 is that, but these interpolation tricks work very well. For example, it has been key to prove Parisi formula, okay? The first idea of Talagrand was to interpolate the Gaussian, and continuous time, it's easier than discrete time, so now I have a tool to use because I have this time to do some computation along the time variable, okay? Here is not very interesting because it's nothing happening in the time variable, just the variance increases, but somehow I have Brownian motions now, for which I can use Boué-Dupuy formula. So now I want to represent this. So this is a functional of a Brownian motion now, because W is a function of the Brownian motion. So think about W1 to be essentially some functional of a bunch of Brownian motions, okay? So now I have a functional of a Brownian motion, I can apply Boué-Dupuy formula, okay? So you apply Boué-Dupuy formula, and you get a formula like this for this quantity. Let's call let's call it Zt, okay? So you get minus log of Zt is equal, okay, let me remove lambda because I'm not using right now. If you want, you can put lambda here, but it's not very important for, okay, maybe let me leave it here. Sorry. So remember what it was, but now I write in a different way then we discuss. So this is the inf over processes Z. No, sorry, now I have too many Z. That's not good. Let's call this object exponential minus ft. No, I have too many f. Okay, let's not give a name. Let's just, letters are finite. I have to use color, but let's put it again like this, so I don't care. It's this quantity. You have the formula, I just write it, let me write it here, it's important. So is an inf over certain z, and now this is the expectation. So now I will not change measure. So I don't write, if I don't change is the law of this, okay? If you are not sure, you ask, please, but somehow is the base measure. Then I have, so let me write a formula, then we discuss. I have Vt of W1 plus Z1. I write a formula. So you you have to shift, here there is a subtlety that what you have to shift are the Brownian motions. So are the Brownian motion who get shifted in the Dupuy formula, but then W is just a linear function of the Brownian motion, so also W got shifted. So I call Z the result of this shift, okay? And then the entropy, which would depend on U, on the shift I'm doing, actually get this form. It's, I call it E of Z, okay? And here I optimize overall Z, which belong, essentially Z belong, let me write something. So H1 in the time variable and H1 in the space variable. Okay, these are the Sobolev spaces. Okay, Z, now you say, well, what is the Z? I mean, but you have to imagine that Z is what you have here. So essentially Z will be, you have to imagine Zt is like 1 minus Laplacian minus 1/2 of Ut. Ut is the shift you have, okay? You see, you have a branch of Brownian motion and you shift them, and you have a U, and U has, essentially this U will be a function from, essentially U will belong to L2 in the time variable and L2 in the space variable, okay? This L2 is exactly this space here. Because when you shift a bunch of Brownian motion, essentially you shift this object by an L2 function, okay? This, here. You shift this object by an L2 function. Let's not, so essentially B gets shifted by the integral of U, like before, and Z gets shifted by U, but with this, so I compute the derivative, okay, of Z. So U is in L2, this object gain U1 degree of regularity, so this object is in H1, and then you integrate, because Z is the integral of U is in L2, so you integrate, here you apply this operator, and here you apply the integral operator, and then you gain 1 degree of regularity in both variables. Okay, so instead of optimizing over U adapted, I optimize over Z, which are adapted. They are in H1, so they are even continuous. And you have a formula like this. So the only thing I need to tell you is what is E of Z. So E of Z would be the L2 norm of U. So 1/2 the L2 norm of U in time and space. And then it will become, so I want to write it in terms of Z, so it will become the norm of Z in H1. I don't want to write it in this way. It's the norm of Z dot in L2 of time and H1 of the space variable. Okay, now let me not write it in this way either. So let's write it here, maybe. Let's write it here. So E of Z, I think a good way to write it is just, let's write it in this way. The integral between 0, 1, and then the operator 1 minus Laplacian 1/2 applied to Z dot S, and then you take L2 norm on the torus. So here I write this, since I don't want to write the torus, usually maybe I write in this way. It means you take L2 norm in the space variable, and then you integrate over S. Okay, so it's the L2 norm in both space and time of this object, because this is what would be the drift. Okay, what you give you the drift. Okay, so I write E because this looks like a Dirichlet form. So somehow you're taking the derivative, but it's a you take both derivative in time and space. Okay, it's a strange object. It is what it is. Okay. So this is exercise. If you want, you take Boué-Dupuy formula, you apply it to our problem. This is going back to what Carlo was saying. Okay, I'm applying to an object which is not exactly a Brownian motion. W is a linear transformation of a Brownian motion. So you get some changes in the formula. In particular, here you don't get pure L2 norm, but you get the natural covariance of the new process, okay? This is very easy. If you do for SDs, the entropy will involve the parameter of the SD. So that's always changes. And now we have the Boué-Dupuy formula for that. So now I could try to redo the exercise for us is, if I was not Nelson, but I was Boué-Dupuy, how I would prove integrability of this object. Okay, I show you Nelson proof because now I want to make comparison with how you prove it in this approach. It's not necessarily shorter, but does not mean that it will not go farther. Okay, you see my point. Okay, it can be adapted to situation where you cannot adapt the other method easily. Okay, of course you can adapt, but it requires a lot of work, but also it really different proof. Okay, so let's see the proof. I want to prove this. I want to use this formula to have an upper bound. So actually, yeah, this way of writing the formula. Okay, since I wrote it with the inf, what you need now to have an upper bound on this quantity, you need to have a uniform lower bound on that quantity, okay? Because you have an inf, so the difficult direction is to prove that the inf does not go to minus infinity. Just to understand, I have a feeling about this formula. Since it's an inf, you have an easy upper bound because you can put z equals 0. And if you put z equals 0, you just take the average of v. And this is Jensen inequality, okay? You take this expectation in the exponential is convex, you get a lower bound. Okay, so Jensen inequality corresponds to taking the trivial competitor in the variational problem. But of course, if you want to have uniform integrability, you have to prove that you have a uniform lower bound for this quantity. Okay. So now let's try. Okay, now you have to understand. We have to do something because you see here now the logic is different. I don't try to understand what is this random variable. This was the logic in Nelson proof. I try to understand what happens to that random variable. First of all, the random variable is not anymore in the exponential, so this simplifies a lot the problem. But of course, you pay a price. That is, you don't have really it's not the random variable what you care about, is what happens when you shift the random variable. Okay. This is this Lipschitz property is also in just a lecture where if you have a Lipschitz function, you have Gaussian tail. I showed you how to prove it with this formula. But here the idea is that to understand a random variable, you have to understand what happens when you shift the base point. And this is not very common in probability theory. It never happens, okay? So the logic really starts differently. So let's look what happens when you shift. You see, the cost is a function of the terminal value. So somehow I know that the optimal control is Markovian, but I will not use this, okay? But I don't care, actually. It's not needed. Okay, so now we have to understand what happens to, this is a fourth order polynomial. It's easy to see what happens, but there is a magic thing happening here. And the magic thing is that if you do the computation carefully, this will become lambda, the integral, and inside, you see, it's a fourth order polynomial. So you shift, you get a sum of terms. But then the magic thing that happens is that, yeah, it's a bit annoying, the notation. So certainly you have a term which you have the 4 power of w. Yeah, I'm annoyed by the notation because I will have to. So you have W1 regularized, and then you take, so this t is not a time, it's just my regularization parameter, okay? So let me ignore this because trust me that it will work, but if you are, let's take t plus infinity. We know that this random variable existed, so I remove one parameter and I just have to prove that this thing does not go to minus infinity, okay? So I will have W14, this is just when you don't have anything. And then this is a magic thing, it's not obvious. What will happen is this, okay? This is a property, well, I need to compute so this is 4, I guess. Then there is 6, you get, are they correct? Who remember Pascal's triangle? Yeah, thank you. Then I have W1, Z1, and then I have Z1 to the power 4. Okay, so what happened here? So this is a computation you can check. I invite you to do it. If you take an Hermite polynomial and you shift it, you get a combination of polynomial, but they form again Hermite polynomials. Okay, you see? Remember, this was a notation with for a particular fourth-order polynomial. You shift it so you get a bunch of lower-order terms, but you can arrange them so that the W1, the powers of W1 always appear as Hermite polynomials, and there is no other infinity, no other contribution popping out. Okay, it's exactly like this. This is a magic formula. I mean, either it works or not. There is no reason in this lecture why it should work. We take it as good luck and good omen for the future, so this is good. I don't know. I don't see any particular reason that should happen, okay? Because you see, these are orthogonal. You are shifting, you are outside the setting where the Hermite polynomial makes sense, okay? We define them as orthogonal polynomial of a Gaussian, and now we are shifting the Gaussian from an arbitrary quantity. It's nothing to do. Maybe if you have a reason, I would like to hear, okay? Just, you are here to improve the lecture notes. Not as passive bystanders, okay? So this is the shift. So you see the shift show you other properties of the Hermite polynomial that we didn't saw yet. And now, remember that we know the regularity of these random fields now. Remember that all these random fields, essentially this is Gaussian free field, so all these random fields belong to C minus kappa. Okay, let's fix a kappa positive, very small, and all these random fields belong to that space. Okay, these are distribution. And now what you know about Z1, well, Z, you know that is in H1 of time, so it's a continuous function of time because H1 embeds and H1 in space. So Z1 is H1 in space. Also because essentially this norm enforces, so the cost function now is the regularity of Z. Okay, this cost function controls the regularity of Z, so you can assume you are in this space at least. So this cost function is finite pointwise, then you need to average it. So certainly I would like to assume Z1 in this space, and now you have a problem in analysis. Okay, so this is the potential, and you want to avoid, you keep this cost finite, and now the question is, if this cost is finite, can I make this potential arbitrarily negative, okay? And you see, you have so this object, actually, we don't care about. This is the first object, which was the main subject of the Nelson proof. Here, I can drop it, because this object will not influence the infimum. It has average 0 under the measure. Actually, I can drop it, okay? You have to take an average. So this object does not depend on Z. So you take the average. Hermite polynomial are normalized, are orthogonal. This is 0. Okay, so this will not influence anything. So this one, and then you have a good news. So the good news is that now you have a term which is positive. These are not positive. Remember, our problem is that the renormalization made the things very negative, but you have a term which is positive. And of course, this is the sign of W, of V. Okay, if you change the sign of V, this term will become negative. So the sign of V, which was, I remember, okay, is the test, is the mental test to see if you're doing the right thing, because with the Bronx, there is a minus, but if you put the plus, it should not work, okay? Whatever you do should not work because it's not integrable, actually. So here, what is going to change is that this become from good to bad, okay? Because if it become negative, then you can have a function which is in H1, but it has very negative, well, probably not, actually. In this case, you cannot, because, well, you can actually, because the problem is not the regularity, of course, because L4 is controlled by the H1 norm. But the problem is that the H1 norm, you have only homogeneity 2, okay? And here you have homogeneity 4. So if you enlarge your object, this increase to the power 4, this increase to the power 2, so this can never control this term if this term has the wrong sign, okay, just by equation of homogeneity, okay? But again, think about what we are doing. We are not doing probability theory, we are doing analysis now, okay? I'm sorry for those who, so we converted now problem probability theory become a problem of functional analysis is, can this function be controlled by that function, okay? Like functional inequalities, okay? Now we disregard all the probability, we used only probability here, so we use probability because you need to prove this, that this is almost surely bounded and there's some moments, and this is the only use of probability, and we will use only analysis. So let's see. So we look at them you have to look only at the negative term. This is a good term, okay? This is good for you. You don't care about it because it's positive, but it will help you actually, because then you will have problems. But let's look first at a term which does not have problem, this one. So let's look at integral of W1, Z1. This is integral in space, of course, okay? Space is the top. And now I want to prove that this cannot be very negative, okay? Cannot be made very negative. But the argument is the same somehow. This is linear in Z. I want to prove that this cannot go more than the other term. There is the space dependence, but now this is a duality between a distribution and a function, so you put them in dual spaces. Essentially, you can put W1, okay, when you do, this is a duality, okay, so this is in H1, you can put this in H minus 1, but actually for this object, you know a better space, so you put it in the space where it belongs. This is the best estimate you have of this object. So now, what happens to the other object in the duality? So this is duality. If you put this object in this space, it means that he has integrability L infinity. So you can put this in a space where you have integrability L1. And since this is a negative regularity, you can put it in a space which you have positive regularity. Okay, so you have to put this in B kappa 1, 1. Okay, so this is the duality. Remember that this is Bezoar space minus kappa infinity infinity. And the duality relation between Bezoar spaces is trivial, okay? Every index got its dual, and the regularity get the negative of the regularity. It cannot be simpler than that. And it's sharp, okay? This is really the duality. So this space is dual to that in the sense of functional analysis, okay? Well, no, maybe not infinity, infinity, but the intermediate ones. Okay, now what you do. So you are interested, now it's very easy actually, because so you can increase the integrability. You are on the torus, so you can increase the integrability. So this can become B22, and since kappa is very small, here you can put 1. So you can bound this with the H1 norm in space, okay? Because you can put 2. So I can say this is bounded by W1. Yeah, I'm sorry. I mean, I learned this thing when I needed to do this computation, okay? So, but there are very few basic things. If you are you have to remember very few things. I mean, if you are in a compact space, in a finite measure space, let's say, you can increase the integrability index, okay? Because you use essentially Cauchy-Schwarz, whatever inequality you like. So you have an embedding of this into Z1, B to 2. You can increase this to 2 because you are on the torus. You can increase this to 2 because the smaller L spaces embed one into the other. Actually not, you cannot, sorry. But you can increase by losing a bit. So let me lose a bit, so I'm sure I'm saying something. Okay, the second index is not important. So if you lose a bit, you can increase. Yeah, otherwise it would not be correct. Sorry, because L2 is not. But anyway, something like this, and you have a lot of space because kappa is very small. So this is now an Hilbert space, and is the Sobolev space to exactly or equivalent to the norm in the Sobolev space to Aka, and here you have H1. Remember, here essentially this norm is like the norm in H1. Okay, so you can replace this by H1. and you have a bound, okay? Unfortunately, there are a lot of this computation to be done. This is not make this proof somehow not as simple as Nelson proof. You need to know a bit of functional analysis, but the idea is simple. That is more or less you have this is regular, this is irregular. As long as the irregularity does not beat the regularity, you can work out. Sorry.
Why I do this? Because shouldn't it be in the like coming polynomial like situation should be W1, Z1, circle?
I'm looking at this term.
But shouldn't it be to the power 3?
I'm looking. Yeah. You're right, sorry. I don't want to look at this term. I'm looking at this term. But is this, thank you. Yeah, sorry, I made a mistake. Actually, this is complicated. Seems easy because, well, this is complicated because this power starts to be very near. Okay, this I will look later. Sorry, I'm looking at this. Thank you for the remark. So I'm looking at this now. And it does not change anything. Yeah, sorry. But because the proof is the same, that's why I didn't detect the problem. Sorry, but let me look at this one. Yeah, thank you. I was distracted. Okay, so this is easy with respect to Z because it can be controlled by second power. Okay, remember this argument with the Lipschitz function. So you have an object like this, and now the other trick we use is that when you have so here you have an object which you know very well, and this you don't know because it's your trial functional, so you don't know anything about its probabilistic structure. So you split them. You use Young inequality to write it as a sum of two things. So remember, you have things like this. AB is smaller than a squared plus b squared. Maybe there is up to a constant. Okay, there should be a 2. But actually, what you can do in general is that you can make a large power a small power, and you can put a large constant a small constant. Okay, so you want to put this object, so you will have, now this gets annoying. So let me use, I will have to write a lot of those objects. So let me introduce by now the notation that when I write Wn with double bracket is just something like that. Okay, maybe there are coefficients because I want to remove this coefficient, but let's forget about the coefficients. I write like this, okay? So this is equivalent to that, up to some coefficients, okay? So this makes my notation better. So here I have W3 in C minus kappa. Here I can just do that, okay? So I take the square with a large constant, which depends on this small constant delta here. And actually I want an equality here because now constants start to be important. And here there is Z1 in H1 with the square, okay? And now you see that this term cannot beat this object, okay? So this term is under control. So I will show later, but essentially for this term, we are done, okay? This is good, I'm very happy because you lose a bit of the energy, okay? This costs a little of the energy. So the energy, this cannot be very negative because the energy will push this up again, okay? The sum of this and the energy is positive, bounded from below, is bounded by minus this object, which does not depend on the controlling, and this is integrable, okay? This is in L1. So this is in L1 of my probability space, okay? So this is okay. Yeah?
You are not even using this Z1 term.
No, for this is the easiest term. I don't use because you see this is linear, so I can always, I will have to do Young inequality, so you have to be ready to lose a bit, but here I have a lot of space. Of course, this term is trickier now. Here I don't have any space at all because this is already, it's the homogeneity problem here, okay? This is the large field problem. The large field problem means, you see, among the problem I listed at the beginning, this is, you have to care about large fluctuation, which in this variational approach means what happens if Z become very large, and is a question of homogeneity. You multiply Z by 1 million, this grow fast, this grow as that, and this grows faster. So these two terms, this term you don't care, or actually you help, now you need it, because you have to use this to beat the homogeneity of these two terms. And you have to use this one to beat the regularity, because this has no regularity. this does not give you any regularity, so you have to use this for the regularity and you have to use this for the homogeneity. And you cross the finger and hope that everything works, okay? Unfortunately, I don't have a general theorem, so this would be open problem for you. We will have to do computation for each of them. It should be true that it's true, that it will work, but I don't have a way to see automatically. But okay, this at least bit of function, but this is functional analysis, okay? We are doing PDE estimates in some sense, okay? Okay, so this first term, I didn't insist very much on this, but Justin is correct. Now we have to work harder, so let's look at this term. Let's do the best I can. So second term. Second term is, this one is something like looking like W21, Z21, okay? And now I want to abandon this. And the logic, at this level, the logic is the same. Here, essentially, you don't lose anything because this is a tight inequality, so you can continue in this way. So you have to do this. This is no-brainer. But now you have Z21 in B11 kappa. So you see, you need regularity, you need, and this is already more or less in an L2 space. You see, this cannot be controlled by better than L2 because it's already an L2 norm in some sense of Z, okay? So here you are at the boundary, and here you cannot hope to complete because this regularity will also eat a bit of integrability from you. So you cannot, so sorry, you have to split these two terms. So you will have to lose anyway by Young inequality. So this is already homogeneity too, but when you do Young inequality, you lose a bit of homogeneity because, let me write it. I write it here, good. I found a use of this step. Essentially, when you have a product, you can always, let's say, put a small constant here, a large constant there, and then you bound, and then there are other constants which I don't remember, but essentially you can take Cp over delta P, AP, and another P constant. Maybe you remember the constant, I don't. Is 1 over P and 1 over Q, maybe. BQ, delta. Here, delta, you can take a power 1, I think. No, actually, no, I don't remember. It's not very important. It's not very important to me. I will know. So it will be like this when P and Q are conjugate. So, but then it means that this has to be always bigger than 1. Okay, so you lose always a bit. Okay, you can take this near infinity. Well, you cannot take infinity, of course, because you see this is a random variable. So, okay, it depends how you do, if you do before and after taking the average, but you could do also in the average, okay? So this is your choice, but essentially I don't want to do infinity because this is not a bounded random variable. So you lose a bit anyway. So here you don't have hope, and you do a bit of computation. I will not do because I will lose you and myself in the process, but you proceed with some functional inequalities, and then you realize that this object is controlled by pathwise, so I'm not using any probability here. So here there is some lines of functional inequality, but they proceed in similar fashion. Just you have to be more inventive about functional inequality. It's on the notes. You have C minus kappa with some power. I don't remember, it depends, because you have to take power bigger than 2 to have a very small power here. And then the important thing is that you have a similar structure, but here you lose not only the H1 norm, but also the L4 norm, okay? So here you will have something in H1 to the square, and then you have Z1 to the L4 to the power 4, okay? So this is, let me, okay, half an hour. I think we are. Okay, so this is an exercise in functional analysis. Every paper, I cannot decide what is the best way, and my co-author in the papers, Nikolai Barashkov, also has everybody has its own preferred way to do it, but the start process has to be here, the end process has to be here, and then in the middle there are various ways to use different functional inequalities to get there, okay? I didn't find any good way to do it, so it's a bit unpleasant sometimes. Okay, yeah, here you have to use, okay, let me give you just an idea what are the ingredients. Okay, here you see you have you know Z, you know properties of Z, but here you have a function of Z, and then you want a positive regularity norm. So somehow you want to take fractional derivatives of a function of Z. Okay, here you need to estimate this. So you need, for example, for this, you need a fractional, how you call it? I don't remember the name. Fractional something. Sorry, it's the fractional, yeah, you need to be able to take fractional derivative like with a fractional Leibniz rule, sorry, okay, yeah. Okay, so, okay, this is a name. What does it mean in concrete? In concrete, it means that if you need to take, if you have product of two functions, for example, and you need to take some norm like, let's think about, for example, let's take this, okay? Or let's take 1, 1, for example, okay? I give you an example, I'm not using. So what does it mean? Fractional Leibniz rule is that you have to take k derivative, k is a small number, of a product. So what is Leibniz rule is that if you take one derivative, you have to differentiate one and make product with the other and the other way around. So fractional is the same. It works the same, up not algebraically, but in the estimate. Okay, so the estimate for this is f estimated in b kappa. So now you take the derivative of f, and then integrability. Of course, here you have to choose how you split the integrability between the two functions. Let's say I take 2, but I could take any other exponent. And then you have g, and then g can be taken in L2. Okay, so g, I don't need any regularity. But then you have the other part where you take the regularity of g. Well, you have to do the other way around, okay? So at the end of the day, what you can say, so either you want to do this when it messes up life. So essentially you want to do, yeah, no, it's a bit better actually. It's really that. So let me, because I need something like this. So it's one of the two functions is differentiated and the other not. Okay, so this is important for me that if I have two functions, I should not need to require regularity from both functions. This is very important when you try to prove things like this, okay? Because otherwise you are screwed essentially. Yeah. Maybe I should not say that word in the recording, but okay, whatever. It's okay. So this is a comment. If you are not interested, or if you don't have brain power to think about it, don't care. I think the main message is that you can arrive here and you can do it. So this is the most difficult actually of the term because it's already power 3. So you don't have a lot of space to make errors because you can only, you see, you want to have only a term like this. But essentially it can be done also for the last term. So let me cancel here. So for all 3 terms, you have this estimate. Okay, and this gives you, okay, therefore we know that W infinity, so V infinity of W1 plus Z1 is bounded from below. Okay, this is a one-sided bound because there are no upper bound, but it's bounded from below by minus sum of things like this. So there will be a sum over n from 1 to 3 of some norm of Wn to some power, which I don't care because these are all the power. They are only with some constant. So it's bounded from below from minus constant this plus good terms. Okay, so Z1, H1, Z1, L4, 4. Okay, this is exactly the integral of Z1 to the power 4. Okay, there is nothing mystical about it. And is that, and of course, why there is a small power? Because essentially in a lower bound, I can ignore this term. Actually, maybe I want to keep it. So all these residual terms are bounded like this. And then in the lower bound, you can put it with the positive power and size 1. So it's there. L4, 4. Okay, so it's like this, the lower bound. Sorry, this is a minus. Yeah, these two are minus, this is a plus. Okay, because it's this term. So in the lower bound, it stays like it is. And for this term, you take the worst case, which we estimated. And so they come with the minus term. So now if you add, now if you add the energy is an upper bound for the H1 norm. So this I didn't prove. So here you can also add the H1 norm. This is exercise for you if you want to understand a bit the logic. Maybe this is an easy exercise. Prove that this energy bound from above the H1 norm of the end value. Okay, it's just a very easy inequality. Okay, but this is, so prove that, prove that Z1 to the power H1 is bounded by, to the square is bounded by this energy form. Okay, so now we are done. You see that these two terms are bounded by those, but this is with minus. This you don't care because it does not depend on your control. It's a constant as far as you're concerned. You just want to prove that you cannot choose Z so that this is lower bounded. Now you see that the sum of all these terms is positive. Okay, so the sum of all these terms is positive. So now you know that all this guy, so all the guy is bigger than minus this constant. I call it minus Qt. I call Qt any quantity which is in L1. Okay, minus, in L1 of the probability space. And independent of anything. So when you take average in the Boué-Dupuy formula, this gives you a lower bound. And so this replaces Nelson proof, okay? Questions? Yeah? Sorry? Well, I can do this computation essentially, I can do in the limit because you see, what I really proved is that these functionals, these are bilinear, multilinear forms. So what this really proves is that these functionals are bounded in the respective spaces. So you could prove now, if you want to be maybe more safe and or somehow give a rigorous proof, you put the regularization and you pass to the limit, but then all this is stable in the limit. So I do the computation in the limit is the same. Sorry, there is no t. So this is just a number which, sorry, thank you. But you could do in the prelimit and then this proof that all these objects are continuous, or this can be modified into a proof of continuity because they're multilinear forms. And and the lower bound is uniform in the cutoff, essentially, okay, because I did it only in the limit, already at the limit. Okay, so this replaces Nelson proof on a bounded set. So you can say, certainly it's a different logic. It's a logic coming from functional analysis and non-probability. I never use hypercontractivity, for example, because there is no need, because I need to prove that the power are bounded, but this is more easy proof than prove hypercontractivity, or maybe not. I'm using actually hypercontractivity to prove that. So you can question, but somehow certainly not the precise form of the hypercontractivity with the constant, okay? So, but the point now is, this I showed you the logic, and now we want to use this to solve more difficult problem, which does not have an equivalent in the other language, easy equivalent. So what questions or remarks? No? I skipped the functional inequalities. You can look in the notes, but the logic, I mean, you can do in different ways. These are like technical details, I feel. Okay. So I have 15 minutes. Okay, let's try to go on. Cancel this part. So the large field problem has been solved by using the potential itself to bound the large fields. Okay, so you see, I'm using this to bound the contribution coming from the renormalization. So the your potential is convex at the beginning. The renormalization creates your problem because make it very non-convex and very negative, actually. And you have to solve the large field problem, which in this case we solve via these coercive terms. Now, so the next thing I want to do to show you that this technique has some value is to look at 542, or essentially I want to look at 542 in infinite volume. Okay, so I want to take the full space. Okay, this is a problem which has no obvious solution because the formula for the density does not work in infinite volume. Okay. So what you have to do is that you take, essentially the idea is that you take a finite volume, and then you send a finite volume to infinity, okay? And you look at measures like this, which have a density with respect to the Gaussian free field to be given by the exponential of minus V O lambda phi and V lambda. Now the parameter is not the regularization. We understood how to do the regularization. Let me forget about regularization right now. Now I care only about the volume, so let's use the volume. And here you integrate over this volume, but this volume now is a subset in R2. And you see it as a parameter which goes to infinity, okay? And then you integrate the usual thing, okay? So the potential of the field is just the fourth order polynomial. Okay, again. You can do this in 2 dimensions, okay? In 3 dimensions, it will be more complex. We don't do the infinite volume limit, but now the problem is I want to understand this family of measures. Okay, let's say I want at least tightness. Okay, so I have a family of measures. Essentially, the only thing that changes is my density is becoming smaller and smaller in some sense. Okay, this is has to be normalized, of course. So I want to understand this problem. And now you see that there is no hope to use Boué-Dupuy formula directly to understand this problem, because certainly all my quantities become infinite, so it's not clear exactly what should happen. Actually, I'm more ambitious. I not only want to use the formula to prove bounds, I would like really to pass to the limit in the variational formula. Okay, that's the ideal thing I would like to do, but the variational formula has no meaning. So, has no meaning in R2. Okay, so that's the problem, okay, because it involves integral over the full space and they are infinite. There is no reason they should be finite, okay? So you have to find a replacement, okay? We need a replacement. Okay, and the replacement, so actually we were stuck a bit, but then the answer is easy, like every time you understand something. Now before it's impossible. Then you say, no, but it was so easy, why I didn't thought about it. So what is the replacement? The replacement is that this is common theme of this lecture in the last today, because we are looking at the first order condition for the minimizers, okay? So this would be like Justin yesterday used the first order condition of the minimizer to get properties of the minimizer. and we are going to do the same. I assume, therefore, that my problem has a minimizer. This needs some work, actually, because it's an infimum, and in general, it's only an infimum. But then you can relax the problem, work in the space, like you relax optimal transport, you go in the Kantorovich formulation, and then you have minimizer by compactness of the space of probability measure. Let's forget about this. Let's assume we have a minimizer. I want to understand first order condition. So I call it Euler-Lagrange equation. I don't know if... So this is first order condition, just, okay? For the minimizers. Okay, so we have to understand in Boué-Dupuy formula what is the first order condition. Okay, remember that the variational functional is a function of your trial, depend on the potential if you want, and the function of the trial is the expectation of the potential. Let's say I have a bounded volume, so let's call it F lambda. Then you have to shift the Brownian motion, and you have to add this quadratic form, which the potential only depends on the terminal value, but the quadratic form depends on the full path, okay? So this is a variational function, and let's assume I have a minimizer, and I do a small variation of the trial functional, so I should get 0. Okay, the idea is that, therefore, if Z is a minimizer, optimizer, let's say, then you have a first order condition. Here it's just, let me write it in this way, it's Z plus sigma some trial direction, so you make a variation in some direction, and the derivative in the parameter sigma 0 has to be 0. Okay, otherwise you can find a better object. Okay, this is trivial, and everything is trivial, just to give you some kind of equation that you are not used to see. So let's try to write it down. So what will happen? I'm accumulating all the things there. Let's check time because it was late, and I think I can write down. I had 8 minutes, so that's fine. So you do this computation. It's explicit. So these are polynomials. This is a function exercise for you. The first order condition. Let's say I write Euler-Lagrange equation. It looks like this. You have an expectation, and you optimize over adapted control. So you have to, the tangent space is made by adapted control, okay? It is in H1, so it's a vector space, it's fine. You can do this variation, but you have to take adapted control. So Euler-Lagrange equation looks like 0, so you differentiate. So what will happen here? You take the derivative of the function v. So let me just write, this is like the gradient of v on Z1 in the direction of K1, so it will be something like this, okay? You have to integrate essentially, okay? So you integrate over all space, you can represent the gradient. No, let me write abstractly. So it's just the variation in this direction, okay, of the potential. And then the form E of Z, it's a quadratic form in Z, so it's an easy computation. It will be, I write it in this way, is twice EZ, EZK. Okay, so this is a bilinear form, so I just write explicitly that depends on the two things. Yeah, thank you. Yeah. The gradient is W1 plus Z1 because the potential, sure. Okay, now I write down explicitly what does it mean. Let's write down there is expectation. Unfortunately, you see, it's not a pathwise condition. You have a mean because your functional is a mean. So you differentiate the potential. The potential was the integral. Then you just a pointwise computation, and a property the property of Hermite polynomial is that when you shift, you get another Hermite polynomial. So you get essentially the cube. So let me write in this way. So the renormalized cube, maybe 3 times this, and then K1. And then let me write explicitly the bilinear form. The bilinear form will look like that. 1 minus Laplacian, let's write it like this, z dot s. Actually, let's write as an integral, k dot s ds. Okay, and yeah, here I have object like this, okay? I have 1/2 of that operator, but it's self-adjoint. I put it on one side, and I put it on z, and you have this variational thing, and this is the L2 norm, and in space and time, okay? Sorry, there is, I'm a bit, okay, so it's something like this, okay? It's some more or less exercise for you, but so this looks a very strange, so it's a first order condition, so this has to be true for every kappa. You have to have this condition, okay? It's very difficult to understand what does it mean, but essentially it's an elliptic equation for z. Okay, now you say, okay, well, okay, there is a Laplacian, so let's try, there is a way to write it which is not very useful. Actually, we will use this form to do what we need to extract information, but let's try to understand that it's elliptic, then next week I will show you how to use it, but you now, you have to write in a better way, so let's write it in this way. K1 is the integral between 0 and 1 of k dot. Sorry, k dot is the derivative, okay? The derivative is in L2, so certainly I can integrate it. So, and then you do Fubini, let me do Fubini. So you write this as the expectation of the integral between 0 and 1 of 3 times of the space integral, because you have space integral on both sides, then you have 3 times this strange, this polynomial, but this is exactly an expansion on Hermite polynomial and z, okay, like before, plus 1 minus Laplacian z dot s. All this is multiplied by k dot s, okay? So I have something like this, okay? I just wrote this object in this way, and I put it out. And now I can use that Ks is adapted. Okay, you see, here I could not do anything, but if I write this as an integral, now this is multiplied by k dot s, so this is fs measurable. So I can take conditional expectation here. I can take conditional expectation of this object, essentially. I write yes is the conditional expectation. So let me use this notation. Yes is the conditional, I have a filtration, which is the natural filtration of my process, and I use conditional expectation. So I get an equation, and now I can, since now if you think about it, the fact that this is true for every Ks means that this object has to be 0. Okay, exercise for you, otherwise you can write a Ks for which this is positive. Okay, so essentially this equation means that you have the object inside the bracket has to be 0. You see, because essentially you take Ks to be the same object, which is adapted now because I put the conditional expectation, and then you have the square, and it has to be 0 is 0 almost surely and almost everywhere. And so the equation is this is equal minus 3, the conditional expectation. So sorry, let me write it down, because this is the, let me write it here. This is, I don't know how to use this equation, but it's very nice. It's very minus 3, the conditional expectation of this renormalized potential. Okay, and this is called we call it forward. This is technically, well, it's not, it does not seem like, but it's a forward-backward SD. Okay, so this is an elliptic, you see, it's an actually it's very strange equation because, so this is the unknown. You take the Laplacian, you take this linear operator, you take a time derivative, and this has to be equal function of itself, but this function has to be computed at time 1, and then you have to take conditional expectation to find the drift at time s. Okay, so in this sense it's forward-backward because you need a backward step to come back. Okay. This is score function. So this is, okay, whatever. Okay, oh, I wrote it down. This is what the first order, one way to write the first order condition. So this replaces now the variational problem in some sense. Intuitively, what you could hope, I don't know how to prove it in this case, but what you could hope is that this equation characterizes the minimizer, okay? In particular, if you can prove that this equation has unique solution, then there is a unique minimizer. But even if there are multiple solutions, any minimizer should satisfy it. Okay? So, yeah.
So the lambda disappeared. So implicitly, this is true on your domain lambda, and then you want to say lambda.
Well, this is, so now, yes, sorry, this I forgot about lambda in this. No, sorry, because I made good, I was too fast. I made an error, so now you have to find the error. The error is that here there is no domain lambda. Sorry, I was thinking on the torus, but actually I forgot that so the energy, the entropy is on the full space, remember. So your entropy is in the full space. So you have to control this in the full space, so let me write it better. Sorry, I made a mistake, but this, I think it's good. So that we understand. So the potential are restricted to a bounded volume. The entropy is in the full space because if your potential is on a bounded volume, again, you don't need to do a lot of change to the measure. This is like with the time interval, okay? If you have a cost in a given interval, you don't need to change your process very far because it will not affect the cost. So you hope that this makes sense in finite volume. But then when the volume goes to infinity, somehow you need to change the process everywhere. So if you look at the equation now, here you need to put the full space, but then you have the indicator function of the set here. And therefore, thank you for the remark. Here you have -3, the indicator function of my set. Okay, so the source term in this elliptic equation act only in a bounded set. Then you solve the elliptic equation. So a priori z is different from 0 everywhere. Okay, this is a nice thing. No, I mean, you have your space, you have your set lambda. So certainly you have to do something for z here because you have to compensate this term. And then outside the set lambda, this would solve a free equation. It's a elliptic equation, and you check that solution decay exponentially because you have the mass, so essentially looks like this. Okay, more or less. No, it's not. No, it's not. It's gentler. No, it's just. I'm not enforcing that it's 0 anywhere. Inside a set, you have some force which make your solution have some behavior, and then outside the set there is no force, so the solution decay nicely. It's not an obstacle. Okay. It's something like this, which has finite entropy and okay. I stop here. So Monday or Tuesday, I don't remember anymore. We are going to use this to get a priori. So this is now an equation. You want to get a priori estimate uniform in the volume, and then this allows you to prove. My point is that if this is a minimizer, what is the law of W? Remember, okay, this maybe we will prove. The law of W1 Z1 for a minimizer is equal to my measure. Okay, otherwise doing all this would be pointless. This was implicit maybe in what we are saying, but there is no reason to believe it because I will have to prove it. But somehow, if you have a minimizer, the law of the minimizer represents your Gibbs measure because the Gibbs measure was the minimizer of the original problem. But since we extended the problem, it's not clear anymore that this is still the case. Okay. So this is stochastic quantization. I have now an equation which represents the measure at some value, or machine learning. I'm doing machine learning. This is a generative model for this family of cats, or whatever you think they. Okay? Thank you. Bye.